if you'll recall, last week we talked about polar coordinates and then seemingly shifted gears to talk about complex numbers. Specifically, we talked about complex numbers, what they are. Remember, a complex number has the form a plus bi where I is the square root of -1. That is, I squared is -1. And we also talked about how to operate on complex numbers. And we discovered that operations are just like polynomials, but we can simplify powers of I. So it works just like with polynomials, but we can simplify powers of I. So remember that I is just I. I squared is -1. I to the third is -I. And I to the fourth is +1. Then it just loops back to the beginning. Every four powers, we get a 1. So I to the fifth is just I to the sixth is -1. I to the seventh is -I to the eighth is back to 1. I to the ninth will be back up to I to the 10th will be -1. I to the 11th is -I, and I to the 12th is 1. And this goes on forever. So we want to be able to simplify our powers of I. But after that, but before that, we're just doing polynomial stuff. But we never get powers of I bigger than 2. It's either ±1 or ±1. We can talk about where complex numbers come from. So today we want to talk about that, complex numbers. We want to talk about complex zeros of polynomials. We also might have this in the context of complex solutions to polynomial equations. The complex zeros of polynomials. We can also talk about complex solutions to polynomial equations. Zeros of polynomials are just solutions to polynomial equations. All right, so let's talk about our zeros of polynomials in general. And then we'll talk about the complex zeros of polynomials. I want to start with our most basic one. We got plus and minus 1 for 0. So if we have x squared minus 1 equals 0, this polynomial equation, we can solve this by factoring the polynomial. And then using the 0 property. And so we see that we have these two real solutions to this polynomial equation. We might also say that the polynomial x squared minus 1 has two real zeros. So we could talk about the zeros of the polynomial or the solutions to the polynomial equation. Solutions are equation things, zeros are polynomial things. X squared minus 1 equals 0 is a polynomial equation. If it's an equation involving a polynomial, come up with very clever names in math for things. But we could also refer to 1 and negative 1 as the real zeros of the polynomial. Real solutions to the polynomial equation, real zeros of the polynomial. And we can see they come from the two different factors of the polynomial. So x minus 1 and x plus 1 are the factors of the polynomial. Each of the factors of the polynomial corresponds to one of the real solutions of the polynomial equation, corresponds to one of the real zeros of the polynomial. Just naming a part. Factors of a polynomial, zeros of a polynomial, solutions to a polynomial equation. So we wouldn't want to say something like, solve this polynomial. That sounds weird. We could say, solve this equation, and then specify its polynomial equation by saying, solve this polynomial equation. But we're not solving the polynomial. We're solving the polynomial equation. Any question? That's just how the words work. If you said, I need to solve this polynomial, for the most part, people would know what you're talking about. But you don't want to say it that way, because you sound like an amateur. People might not say anything to you directly, but they'll definitely be making fun of you behind your back. Can you believe it when they said, solve the polynomial? I know, it's like they don't know how words work. It'd be really snooty to do that. I'm just trying to let you know how the words work. You know what I mean? It sounds like saying, I'm going to pilot my car. That's either because you're not really sure how the words work, or you're trying to sound super fancy like some kind of professional driver. You drive at such a high level. It's piloting, not driving. And you'd be like, well, why are the driving shoes called piloti and not drivoti? I'm not wearing driving shoes. I don't have driving shoes. So I'm not fancy that way. You know what I'm talking about? Did you know there were shoes specifically for driving? There are driving shoes. So if you're like a fancy person and you're going to take your Ferrari for a spin, put on your driving shoes. Take the Ferrari for a spin, because that just means you're going to drive it around. But if you're going to take your Mustang for a spin, you're probably going to go to Cars and Coffee, do a burnout and fail, crash into something. You know what I mean? It's just like a completely different movie. If you're a Mustang driver, I'm sorry. Don't turn off the traction control though, until I clear the parking lot. All right, what are we talking about? Oh yeah. Which is weird because my car did get hit in the parking lot yesterday, but it was not by a Mustang. And it's really annoying because the only damage was to the bumper. And in normal situations, especially with modern plastic bumpers, I could buff out the damage and just kind of like push the bumper back into place because it's just a big chunk of plastic, right? But bumpers are now required not just to be there. There used to be a law. The law said if you've got bumpers on your car, they have to be able to survive a hit at like 5 miles per hour or whatever. And then they would bring the car in, say, do these bumpers qualify? And they would get a big machine and they would smash into it, the bumper, at 5 miles an hour. And say, is there any damage? If the answer is no, bumper's okay. If there's damage, this bumper is not sufficient. Now, getting bonked at 5 miles per hour is not a big deal for a plastic bumper. It is a big deal for the sensors that keep you from backing into things. So what should be just like, oh, just like pop it back in, buff out the paint that got scraped onto it. Now it's going to be a costly repair because it knocked out one of their backup sensors. You know what I mean? This is the part of the car that's supposed to get hit. And we put expensive parts in it because we kept backing into shit. You know what I mean? It's ridiculous. I mean, I'm not complaining. I'm kind of glad I have the sensors, but there's also a camera back there and I can see how close to things I am. It's also really funny to watch people backing up a modern car with a backup camera and still like, oh, no, I'm too close. And you're like standing outside for you've got 3 more feet. And they're like, oh, no, and then they start going the other direction. Come on. What are we talking about? Oh, yeah. All right. Right, we just want to make sure we get the right words. That's what started this whole thing. So factors of the polynomial, zeros of the polynomial, solutions to the equation. Now, this is not the only way that we might solve this equation. It happens to work here because I gave you a factorable polynomial. We can also solve by doing inverse operations in reverse order in this case. So we can also solve by saying x squared is equal to 1. So x is equal to plus or minus the square root of 1. So that would be another way to solve this particular equation. So this polynomial has 2 real zeros. We know that if I change the x squared minus 1 to an x squared plus 1 and put that in an equation, x squared plus 1 has 2 complex zeros. It has no real zeros. This solution will have complex solutions, but no real solution. When we learn about factoring, we learn that a polynomial of this form, the sum of squares, is not factorable. We're told that this is a prime polynomial, that it is not factorable. But we're not given the whole sentence. We're just told that this is not factorable. We're not told that this is not factorable over the real numbers, because it is factorable over complex numbers. But let's solve by doing inverse operations in reverse order. I can subtract 1 from both sides. Then I can take the square root. And so x will be plus or minus the square root of -1. And that means x is plus or minus I. Because I is the square root of -1. It's bad grammar. I am the square root of -1. So we know that x squared plus 1, the polynomial, is not factorable with real numbers, but we can factor it with complex numbers. That's the part that we usually leave off. It's prime over the real number. That means we can't factor it and use the real numbers. But if we let ourselves use complex numbers, the solutions tell us what those factors should be. So I could factor this over complex numbers by saying x minus I, x plus I. If I multiply this out, I should get x squared plus 1. So if I FOIL, x times x is x squared plus ix minus ix minus I squared. The plus ix and the minus ix will cancel out. And I squared is -1. So the first thing, let's cancel that out. But I squared is -1. So we have x squared minus a -1. Our first introduction to complex numbers usually shows up when we're solving quadratic equations. Any questions? How's everybody okay? Everybody still bitter about Tuesday? I think that would depend on whether you saw the announcement or didn't see the announcement. Like if you saw the announcement early, I go, oh, great, I'll just leave now. But if you didn't see the announcement until you've been waiting here for like 10 minutes. And it's difficult because I'm often late. So you're like, oh, maybe he's just more late than normal. I didn't set up a camera to see how long people would stay. I'm wondering if more people just show up before I get here. They just look in the room, see that I'm not here, decide he's probably not showing up, and they just leave. You know what I mean? It's weird because you get this mix of students that have figured out that in college, the press doesn't always take attendance. But in high school, like if you're not there, they like sending drones out to find you. In college, you'll be like, oh, hey, sorry, I missed class yesterday, and I have to like cover the fact like, oh yeah, you weren't there. I totally noticed that. I just totally did. You know what I mean? All right. So I picked these because this is the first time we usually run into complex zeros or complex numbers. Our first introduction to complex numbers usually shows up when we start solving quadratic equations. This is a quadratic equation. It's got an x squared, sometimes even an x in it. And we know that the solutions we can get with the quadratic formula, even though the quadratic formula is kind of trash the way we normally do it. The opposite of e plus or minus the square roots of b squared minus 4ac all over 2a. This is the normal way we encounter, the normal first time we encounter complex numbers. And we can see where those complex numbers are going to show up. There's a square root of b squared minus 4ac. There's a square root with some subtraction in it. That means, I have the square root of a negative number. If b squared minus 4ac is negative, then we get two complex zeros. I made red for solutions. If b squared minus 4ac is less than 0, is negative, then we'll have two complex zeros. Our quadratic equation will have complex solutions. A polynomial is not factorable over the real numbers. I'm not really a huge fan of this quadratic formula, even though it is the one that we've all used, the one that we're probably all used to. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Those are probably the words that you use to remember this. That's not even an accurate description of what we're writing. It's just to help us remember to write this. And this is kind of a terrible way of writing things. I prefer coming at this problem from the vertex form because the variable only appears one time and we can use inverse operations in reverse order to solve. So I could say a times x minus h squared is equal to minus k. Divide by a, so x minus h squared is minus k over a. Undo the square root, the square with the square root, so x minus h is plus or minus the square root of k over a. And so x is h plus or minus the square root of k over a. You may recall, although you might have put it out of your mind, that we can go from that standard form at the top into the vertex form with a process called complete the square. So this is standard form. And the second one is vertex form. process of going from standard form to vertex form is called completing the square. Which is the technique that you use if you want to figure out what the quadratic formula should be. If you complete the square on ax squared plus bx plus c, you get the vertex form, and you also get the quadratic formula. Here's the reason I don't like the quadratic formula in this case. It tends to ignore the symmetry that we have in quadratic equations. We know that the graph is supposed to look like a parabola, and a parabola is symmetric about a vertical line through its vertex. There's a middle, and then we get the same thing on either side. A lot of times people describe parabolas as U-shaped graphs. I don't like them describing them as U-shaped graphs. It's more of a rounded V, because U's kind of go vertical. The two parts of the U, they go vertical. But parabola, they don't go vertical. It's kind of off to the side. It's more of a V, but rounded at the bottom. You know what I mean? So if you want to be like everybody else, be like parabolas are U-shaped graphs, and just everybody's wallowing in the ignorance of that. Or if you want to be more true to the way we write letters, you're like, it's a rounded V. But you don't want to say it that way. You don't want to be like, oh, well, actually, it's a rounded V, because now you're being a jerk. You know what I mean? Very difficult line to cross. Because you know you're walking into the land of the pedantic. And you don't want to lead with, well, actually. But anyway. The idea is that there's symmetry in our parabola, that the vertex is at h comma k, and there's an axis of symmetry going, which is a vertical line through the vertex. Points that are the same distance from the axis of symmetry will have the same y value. So we have points at the same y value will be the same distance from the axis of symmetry. That's how this particular symmetry works. Points that are at the same y value are the same distance from the axis of symmetry. One is in the positive direction and one is in the negative direction. There's where the plus or minus shows up. Here's the plus square root, and here is the minus the square root. In the middle, we've got h, and that distance is plus square root of k over n, or minus k over n. I dropped a negative. So in the middle is h, then we go plus the square root and minus the square root. If instead of writing the quadratic formula the way that we do as one fraction, we might make a better connection if we write a middle plus or minus then the square root part. Just by splitting up the numerator with the distributive property, if I take minus b over 2a plus or minus the square root The reason I prefer to do this is that now our quadratic formula has a minus b over 2a plus or minus some stuff. And from our vertex form, we can see a plus or minus some stuff. And most of the algebra students that I encounter at this point in your mathematical career, we're told that to find the vertex, h is equal to negative b over 2a, and then you plug it in. That strategy should be applied to solving. Find out where the middle is, negative b over 2a, and then figure out how far apart, or how far the zeros are from the axis symmetry, because it's going to be the same, plus or minus. That's the role of the plus or minus. One in the right and one to the left. This is the way I would prefer to solve quadratic equations. I prefer that we think of things in terms of completing a square rather than a quadratic formula. Now there's a question of speed. Wouldn't it be just faster to use the formula? Like, well, speed is not really an issue because if we want to go fast, we'll have a machine do it. That'll be faster still. So speed is not the issue. And also, if we trained on completing the square rather than using the quadratic formula, then we'd be faster at completing the square than we would be at using the quadratic formula. It's always kind of funny when people put up videos where someone's explaining how to do math in some different way. There's like a video of some instructor explaining what's going on. And then someone all snotty pulls out a piece of paper and just multiplies the way they did it. They don't explain anything. They just do the problem and they put their pencil down and act like they're all fast and good at math. All right, well, motherfucker, why don't you try explaining it while you're doing it like the other person that you're saying you're going faster than? And never mind that if you really want to race, go ahead and pull out your pen and paper. Let's race. You want to multiply faster? Get a machine to do it. Speed is not the issue. Stop turning your kids against the school because you're keeping them from learning stuff. And you only do it to try to preserve what little pride you have left in the Department of Mathematics. Because you felt shame when your kid asked you a question in math and you couldn't answer it. But they're only in the third grade. How come they know a thing that I don't know? Like, well, because first of all, you don't need to know. And second of all, it's their job to learn it. You don't have to explain it to them. What we hired a teacher for. Do you know what I mean? I've said it before. If you don't know how to help your kid with your homework, good luck, kid. I don't just swallow your pride and admit that. You know what I mean? If you think that's going to irrevocably damage your relationship with your child, man, you've got bigger problems than math. You've got some serious issues that you need to work out if that's going to be damaging. You know what I mean? Then, of course, people come out and it's like, well, you don't understand because you don't have kids. It's like, well, that means I can be objective about it. I don't have an emotional attachment to the issue. I am capable of being objective where you're not, because you're a parent and your pride got hurt. And if you think I'm making fun of you, that's only because I'm making fun of you, because your third grader is about to dunk on you in mathematics. And you should celebrate that. If I had kids and they're like, oh, Dad, you're slow at math, I'd be like, oh, hell yeah, high five the kid. Because they're doing good. And if they got a problem and they got stuck on it, I would still be like, oh, man, kid, I don't know what my kid's name would be. Man, kid, I don't know how to do that. And my kid would be like, oh, motherfucker, you're a math professor. It's like, oh, I don't know how to do that. And then he would know I'm lying to him or her. They would know I'm lying to them, but they're like, oh, this is one of those stupid teacher things, isn't it? And I'm like, oh, yep, I'm going to get more coffee. You know what I mean? If parents think they have to explain everything to them. You don't. They'll figure it out. That's literally their job to do it. Figure it out. Just go get more coffee. Oh, man, kid, that sounds hard. Good luck. And then bounce. Think about how much more pride and a sense of accomplishment they'll have when they figure it out on their own than if you just did their homework for them. Because if that's your argument, just like do the homework for them then. What's the point if they're not going to struggle? You know what I mean? The struggle is the point. At the end of the class, if I was going to do this like most parents think education should work, I'll just take the final exam for you. Anyway. That's why I like this job rather than a high school job. Because in this job, if your parents call me and say, how's little Johnny doing in school? Well, I don't know. You don't have to ask little Johnny. I'm legally banned from talking to you about it. But he's a minor. Don't care. You're going to have to ask your kid. But he's going to lie to me. I'm like, well, then you fucked up. If you know your kid is going to lie to you, how come you scare them so much that they're afraid to admit to you that they're doing poorly in math? You know what I mean? That's a screw up on the parents' part. You've created a bad situation because your kid doesn't want to talk to you and be honest with you about how they're doing in school. That's a you problem. That's not a me problem. Anyway. It's hardest when you get the parents and one parent knows that the kid is a screw up and then the other parent doesn't. Then you have the parent teacher conference. And I'm like, well, I don't really know how to say this, so I'm just going to say this. Little Johnny is not doing well in this class. It's after lunch and he comes in drunk. And one of the parents will be like, oh, yeah. And the other parent will be like, oh, my stars. How could you tell me such things? Like, well, high schoolers are stupid and they think that you can't smell vodka on their breath. I don't know who told high schoolers this, but it is so super false. And they think they're acting all cool, but they are clearly drunk and or stoned. Like you don't go out in the parking lot and smoke pot and not smell like pot. Like in the movies, you just like wave your hand and the smell goes away. That's not how that works. May have worked back in like the 70s or the 80s when the pot was super weak, but I mean, have you had 21st century pot? People be getting high just thinking about it. Anyway, what are we talking about? High schoolers are stupid. That's what we're talking about. What we were really talking about are complex numbers. And they normally come out from, our first introduction is normally when we start solving quadratic equations. Because we know that zeros of polynomials solutions to polynomial equations. Are related to factors of polynomials. And x-intercepts of the graph of the polynomial. Zeros, solutions, factors, x-intercepts, all tied together. And we know that three things can happen if we draw a parabola. We could have a parabola with two x-intercepts. We could have a parabola with one x-intercept. The vertex happens to also be an x-intercept, and we just have the one x-intercept. And this informs us of the form of the polynomial. If I have two x-intercepts, I'll have two different factors. If there's only one x-intercept, it will be the vertex. And our factors will be a copy. So that x-intercept will count twice. It'll be the square of a binomial factor. No x-intercepts. And our polynomial is not factorable over the real number. Let's take 5. We'll come back and talk about how these quadratics fit into complex numbers in general. Let's take 5. And we'll come back and talk more about complex numbers.